So now we know that the gas part or vapor pressure is dependent on the temperature. The faster the particles are, the more likely there are going to be more fast-moving particles that can escape the liquid phase into the gas phase. So here is a table that tells us the vapor pressure of water. And this table is also found in my room, so whenever we do a lab or if you need this number, please look at Ms. Cottle's table. Okay, so there is this reference table in the classroom, so you can always take a look at it. Alright, so over here, this table shows us that at 0 degrees Celsius, there's enough fast-moving particles to escape and cause a pressure of 0.6 kilopascal. At room temperature of 27 degrees Celsius, there's enough gas particles to escape the liquid phase and give you a vapor pressure of 3.6 kPa. At 100 degrees Celsius, this is also when water boils, it gives you a vapor pressure of 101.3 kPa, and we have seen this 101.3 kPa number before, and that was the 101.3 kPa that also equal to 101 atm, which are both our standard pressure, which is also can be noted that it is also sea level. At sea level, standard pressure exists, which is also 101.3 kPa, which is also 1 atm. So over here, you see these coincidental numbers showing up again. Let me explain to you why this you see a link between these numbers and standard pressure and sea level. But before I do that, I want to explain to you guys how to read a manometer. So over here, it's kind of like your barometer, but it has it allows us to measure the vapor of a in a container. There are two kinds of manometers. There is the closed end as well as the open end, and the closed end is a little easier to explain, so let me start with this. So in a closed end manometer, this is closed, and so over here, this is kind of like your barometer where it is a vacuum inside. And so over here, as the vapor pressure or the vapor particles are hitting up against this surface of the mercury inside, it causes a difference in the temperature, and so the pressure inside is equal to the difference of mercury levels. Yes, so this height difference is the pressure inside. So if this were to be, let's say, about 11 centimeters, that would be the same thing as 110 millimeters of mercury, yeah? And so that will be your pressure, which you can therefore convert into kPa or atm or torr or pounds per square inch. Over here, the openness end is slightly different because there are gas particles outside, and these gas particles is the atmospheric pressure hitting down the mercury levels on the side. There are two different situations provided for you. Here, the mercury level is higher on the manometer end, and over here on this side, the mercury level is higher on the atmospheric end. So let's actually explain this one first. So over here, you can see that the mercury level is higher on this end, which will probably let you know that the pressure is greater outside, hitting the mercury harder on the right end and pushing up the particles here. But there are still gas particles pushing the mercury level down here on this side, but it's just less force on this area than onto the area that is open to the atmosphere. So we now know that it's low, the pressure inside the manometer is lower than the atmospheric pressure. So this is how we're going to calculate it. It's going to be the atmospheric pressure minus the height difference. However, on this end, you can see that the atmospheric pressure is actually weaker than the vapor pressure caused on or put onto this end of the manometer. So in this case, the pressure inside is higher, and so it's going to be the atmospheric pressure. In this case, add to it the height difference, which will give you the pressure inside this container. And this also equals the pressure inside this container. So now, what is boiling? Boiling is a phenomenon that actually happens when the vapor pressure equals the external pressure. So over here, there are atmospheric pressure up here that is hitting down the liquid, and hence, if the temperature isn't high enough, remember that in this chart, vapor pressure of water was only 30.2 kPa, but we know that in this picture, the liquid over here, the vapor pressure is 30.7 kPa, but over here the atmospheric pressure is pushing down the liquid much harder than the vapor can actually escape. Over here though, at 100 degrees Celsius, I know that the vapor pressure of water is 101.3 kPa, and at this point, the amount of atmospheric pressure is 101.3 kPa also, so they equal one another. So the water molecule is just pushing up against the atmospheric pressure, and now a lot of the particles can leave. And then you see that the gas particles that is being heated up, the liquid particles that is being heated up goes into a vapor phase, creating those bubbles inside underneath the bottom of the pot, and pushing, and they kind of are pushed up onto the surface of the liquid, and this is what we call boiling. But let's say that we are at high elevation, and the atmospheric pressure elevation and atmospheric pressure is significantly lower than the atmosphere. Than in sea level. And so over here, now even at a low temperature of, let's say, 70 degrees Celsius, water starts to boil. So even at 70 degrees Celsius, water starts to boil. So remember that at high elevation, water boils quicker, or water boils at a lower temperature, and at lower elevation, where the atmospheric pressure is higher, water has to boil at a higher temperature. So now, what is the advantage of being at sea level? Or what is the advantage of being at Yosemite? Either way, if you were to boil water in San Jose and in Yosemite, which water will boil first and why? Please answer this for me in your journal. And if you were to boil an egg in San Jose and in Yosemite, which egg will cook faster and why? And please respond to this in your science journal. And the last question that I'm going to give you is when you boil water, you see bubbles in the bottom of the pot, and what are in those bubbles? So please answer that for me in your journals, and that is all I have for you